have a few more presentations and 3 open discussions on SAI detection, monitoring, and attribution, on SAI simulations, and then finally on ethical aspects of SAI research. I will soon post in the chat a few things to help us run this session smoothly, a few rules, especially about timing. Not sure if there are any participants who haven't joined any previous day. Please, all the speakers, try to keep the time limit. You selected your own duration, 3, 6, or 10 minutes in the registration form, and that's the time you get. You will get a warning just before, like 1 or 2 minutes before the time is up. And then hopefully when the time is up, you're finished. Otherwise, we'll send you reminders. And in the worst case, we would mute the mic. Everyone, please use the Q&A box to ask questions to the speakers, and the speakers can answer them directly. And in the past few days, we made the experience that speakers or people registered as panelists, they can't post questions in the Q&A box. In that case, please use the chat, and we'll keep an eye on that and make sure these questions are addressed as well. And yeah, with that, we can get almost ready to start. The recordings of the first 3 sessions, you'll find them on the link provided in the email, and today's recording will appear there also reasonably soon after this session. The first session with 1 talk and then an open discussion on strategies for SAI detection, monitoring, and attribution will be chaired by Jean-Paul. And yeah, Jean-Paul, why don't you take over, and then
yes, Mark.
You get to the first talk. Thank you, everyone.
Thank you, Mark. Yeah, so we had a series of 9 talks on Monday on SAI detection, monitoring, and attribution. And today we'll have our last talk on this topic. It's going to be a presentation made by Kai Chi on monitoring stratospheric aerosol changes from solar geoengineering experiments. Chai, you can, as soon as your presentation is on the screen, you can start.
Okay. Could you hear me?
Yes, I can hear you.
Okay. I'm glad to share our work here, and I'm Kai Qian. Next slide, please. Next slide, please. The SAI. Sorry.
Liwa, go back 1 slide.
Yeah.
Guy, can you see the slide?
Yeah. Okay.
Yeah, you can go ahead.
The SAI is a strategy to mitigate global warming. While large-scale SAI experiments face lots of challenges, small-scale SAI experiments should be further investigated, and our work focused on the detectability of small-scale SAI. Next slide, please. Next, okay. We used the balloon data. Okay, we use the balloon data. We use the balloon observations over TP and Boulder during 2019 to 2022, and then we conducted two sets of numerical simulations to separate the impact of volcanic eruptions and any wildfire during this period. And this figure shows the balloon observed and simulated stratospheric aerosol mass concentration and effective radius over Boulder and TP. the green lines shows the profiles of the aerosol observed aerosol mass concentration and the aerosol effective radius, and the black lines denote the profiles of the median value of aerosol mass concentration and the aerosol effective radius over odor and TP. And the orange lines denote the median values of the simulated stratospheric aerosol mass concentration and effective radius. It can be seen that for the aerosol mass concentration, there is a large spread in the UTLS, while there is small spread above 20 kilometers. And if we look at the profiles of aerosol effective radius, we can find that the spread of the aerosol effective radius in the UTLS is much smaller than that of aerosol mass concentration. So if we want to detect an SAI signal, the aerosol effective radius may be more useful in the UTLS, and the Karma model could reasonably reproduce the vertical distribution and the variability of the aerosol mass concentration and aerosol effective radius. Next slide, please. And then we compare the satellite observed aerosol extinction coefficients with the simulated aerosol extinction coefficients. The satellite observations were from the Stage 3 and the Stage 2 observations, as shown in the blue lines. And the Karma model could reasonably reproduce the vertical distribution of the aerosol extinction coefficients. Next slide, please. And then we try to figure out the sources of the variability of aerosol mass concentrations. And then we developed methods to identify SAI signals. For the balloon measurements, we identify the SAI signals based on the aerosol mass concentration and the aerosol effective radius, while for the satellite measurements, we mainly identify SAI signals based on the aerosol extinction coefficients. Next slide, please. And then we conducted 2 series of SAI simulations under the present day condition and clean condition respectively. And the initial condition of the present day simulations contains the impacts of volcanic eruptions and any wildfire during 2019 to 2022. And we continuously injected SO2 into the stratosphere in a 30-day period. We injected SO2 in the tropics at 20 kilometers with different magnitudes. Next slide, please. And then we investigated the SAI detectability under the condition involving volcanoes and the any wildfire. We show the results based on the balloon observations and the satellite observations respectively. The panel A shows the regions over where the SAI signals can be detected under different SAI scenarios, and different colors denote the different SAI scenarios. So it can be seen that in the northern hemisphere, SAI signals with injection magnitudes larger than 0.2 telegram can be detected, while in the mid-latitudes of southern hemisphere, SAI signals with injection rate less than 0.5 telegram cannot be detected, which is due to the impact of any wildfire. And if we look at the results based on the satellite observations, it can be seen that the SAI detectability is much lower, which is mainly due to the sparse sampling frequency. And we also show the results of SAI detectability over 4 regions. Next slide, please. And then we investigated the SAI detectability under a clean condition. For the results based on the balloon observations, it can be found that SAI signals with magnitude of 0.01 telegram can be detected in the subtropics of both hemispheres. And the SAI signals with magnitude larger than 0.1 telegram can persist for more than 1 year in the low and mid latitudes. And if we look at the results based on the satellite observations, the SAI signals with magnitude larger than 0.05 telegram can be detected in the tropics. So it can be seen that the sparse sampling frequency may limit the SAI detectability based on the satellite observations. Next slide, please. Here is a summary of our work. Thanks.
Thank you very much, Kai. We'll give a few 30 seconds for people to read your summary before opening the floor for questions. Okay. I think let's open the floor for questions now. Do we have anything in the chat? Let me check if there is any questions in the chat. For the moment, no question. Please feel free to raise your hands if you have questions. Mark, go ahead.
Yeah, thanks for this nice talk. And I guess your message is that also to detect small deployments, maybe unsolicited deployments, a balloon network of regular launches to see if there's anything there would be even more worthwhile than just the satellites, right?
Yeah.
Okay, thank you.
We have a question in the Q&A. Can local releases be detected or just well mixed global? Andrew, I ask you this question. Can you read it?
Yeah, I can read that question. That's a good question. Can local releases be detected or just well mixed global? I think the local release can be detected, and the research and the results show that when we mainly focused on the SAI detectability after the injection in the 6 months after the injection. So our results show that if there is a large anomalous aerosol mass concentrations, and the satellite may scan over this region, and we can detect this signal. And if the satellite does not scan over this region, and we can't detect this signal.
I see. Penfeng has raised his hand. The thing is, I think we should start moving to the discussion part and maybe try to
I think
include some
Peng
of
Fei may be able to further answer that question. Go ahead and let Peng Fei finish answer that question. He's one of the authors on the paper.
Okay. Then yeah. Go ahead. No, you are muted, Penfeng.
Thank you very much. So we are trying to detect how small the pulse injection we can detect using two sets of techniques. One is balloon, one is satellite. So our conclusion for answer Mark's question, our conclusion is because balloon has the advantage of the side distributions and the high resolution in vertical distributions and also side distributions, so we can detect we can detect smaller amount of injection compared with satellite data. So just one local regional injection, so balloon has a higher chance to detect it if we launch it every 7 days. Compared with H3 satellite. Of course, if you use AMPS, then maybe the result will be different. But anyway, so through the comparison we showed, balloon bound measurements is more likely to detect a small scale SAI experiment. That's the one message. And the second message is for balloon bound measurements and the size, both size and the number concentration or mass concentration are both important. The size, because from CAS, from measurements data, we show that the side distribution, the sensitivity or the spread of the size in the UTLS is really small. However, the mass concentration is really big. So combined with the side distribution data and the mass concentration data, we can detect full profile if the SAI signal is in the lower stratosphere, upper troposphere. That will be very hard for if you only measure the mass or extinctions, then it's pretty hard for you to detect it. But however, balloon bound data measurements can do. So this basically two messages we want to deliver through his study. Thank you.
Okay. Thank you, Penfeng. So let's move on now to the discussion part. What I'm gonna do, I'm gonna share my screen, and because the first session took place on Monday, maybe some people here, especially from Asia, may not have been able to follow all the talks. So to start the discussion, I'm just going to present a very quick overview about what was the main discussions and talks which took place on Monday, and from there we can start the discussion. So hopefully everybody can see my screen. Mark, can you see my screen?
Yes, we could see it now.
Okay. So, so here on Monday we had let me remove the part of Zoom which is hanging. Okay. So on Monday we had 9 talks on strategy on SAI detection, monitoring, and attribution. I would say the talks were divided into mostly 3 parts. We had an overview on past, current, and future stratospheric aerosol. measurements. So in terms of satellite measurements, airborne measurements, and ground-based measurements given by London Ranger. Mahesh Kovilakam, sorry, gave us an overview about the global stratospheric aerosol database, GLOSAC, and their relevance for SAI. We had 2 talks on balloon measurements from Alexander Baron and myself, and talks on stratospheric SO2 observation from the Earth Observation Data Group, as well as an interesting discussion on detectability of SAI using solar occultation, and the importance of maybe having a constellation of solar occultation measurements. And finally, we had a talk by Michael Opfener discussing also future IR limb emission measurements for SAI detection. And finally, Frank gave us a talk on quantifying stratospheric aerosol injection. So without going into too much details about those talks, as I said, so the first talk was really interesting, kind of summarizing an effort which has been undertaken by the stratospheric aerosol activity to actually summarize the current monitoring or current measurements, past and current measurements, and future measurements of stratospheric aerosol. And so, as we discussed yesterday, some of those measurements, especially given some uncertainty here in the US on NASA's budget, may not continue. For example, we don't really know if the SAGE mission will continue in the future. And we already know that some mission that was planned for LiDAR mission, NASA, like Kali, Gola, which was supposed to be Luce, will probably not go on. So the situation is always very dynamic, and I think it's important to remember that. Mahesh Kovilakam gave us an overview about GLOSAC, but also showed the difference between volcanic perturbations after the Onga eruption and after Ruang. It was interesting to see in terms of extinction ratio, which is kind of a proxy for aerosol size, to see how the extinction ratio was decreasing after Onga eruption, meaning that the aerosol produced after the Onga eruption were much larger than the background aerosol. But on the contrary, when you look at the evolution of Ruang, it has the opposite effect. So it's also kind of nice to see the difference between 2 different types of volcanic eruptions and how they can provide some information about how they can respond, how can the aerosol microphysics can respond differently for different types and of aerosol microphysics, and how can this kind of shed light on SAI. So Alexander Baron gave us an overview about the B2SAP network that also, and it was interesting since Keiichi just gave us also some discuss the importance of balloon measurements for SAI detection. Sorry. I would say that I share that point of view, the importance of balloon measurements. I also gave a presentation on balloon measurements we conducted as part of NASA upper atmospheric composition project that we started 10 years ago to study volcanic plumes, and that we continue now. Now, I would also argue that if any future SAI detection, especially if SO2 is injected first, could be very quickly detected by nadir observations. Would probably be the first measurements that would allow, if SO2 is detected and if SO2 is injected, probably the first measurement allowing to detect an SAI signature. And so We had a talk by Anthony Nisek, who gave us an overview of the 15 years data set on SO2 emissions. And followed by that, an interesting talk, as I said, by Anna Lange, who really kind of dig into the detectability aspect of SAI, as it was discussed in the previous talk, using solar occultation. And she concluded that to detect SAI above the background using solar occultation, it would be done at least a month after an SAI injection with at least 1 or 2 with at least 1 teragram of sulfur per year. And the talk again by David Keat gave us an overview about the importance of solar occultation constellation for monitoring SAI, and maybe some interesting funding pathways to kind of promote and have those kind of and support those kind of measurements. On the satellite part, I think it was another interesting talk to kind of assess how future satellite observations can be used to monitor SAI. Michael Hopfner talked about the CURT mission. Unfortunately, CURT was on the final step for potential selection, but has not been selected by ESA. But he showed the importance and the detectability potential of future mission like CURT for detecting SO2 especially, where CURT could detect, based on Wacom simulation, could detect SAI if 0.5 ton of SO2 was injected. And finally, Frank Kirsch gave us a nice overview about the observations needed for SAI deployment, but also raised some interesting concerns about the still many unknowns we have about process understanding that really kind of have an impact on what could be the decision on SAI. Especially, I think it raised the point that stratospheric circulation is still something that is not well known, and so we had a similar discussion with Mahu Diallo yesterday regarding stratospheric circulation. So it's still kind of something that needs to be further assessed. He talked about the turbulence in the stratosphere that is not well represented, obviously, also and not represented at all in the larger scale model like used in GeoMIP. He talked also about the importance of the aerosol microphysics and the lack of the importance of knowing the aerosol microphysics to assess the impact of SAI on radiation and climate, and about the plume evolution and how the plume evolution differ depending on scale. So the scaling aspect was also important. And obviously, just now, Kay discussed about monitoring stratospheric aerosol changes and showed us how balloon measurements are also important for SAI detection. So what we would like to do here is to engage some discussions on this first session on detection, monitoring, detection, and attribution. And I have a series of questions I would like to go through and engage in those discussions. So what do you think about the first question? Are we equipped with enough measurements to detect and monitor artificial SAI?
Well, if nobody's going to say anything, oh, it looks like Mark has his. Go ahead, Mark.
Yeah, okay, thanks, Karen. Yeah, I mean, we do have quite a few satellites and we do quite a few balloon launches to look at stratospheric aerosol from volcanics, PyroCB. And I guess if there ever was a decision by international policymakers to have a coordinated and well-planned SAI deployment, hopefully they would also have the money to fill whatever observational gaps there are. What strikes me is that if there was any uncoordinated deployment by an individual country or other player, would we be able to detect it with our current capabilities? And my feeling is not necessarily, and that's maybe something we need to consider to make sure that we have the observational capabilities to monitor changes from such as I said, uncoordinated deployments. I mean, if any country finds a way to silently put aerosol into the stratosphere without anyone really seeing the airplanes taking off or whatever, it would be good for the international community to know, because I don't think that's a decision that any single player should make. And yeah, also not only the aerosol itself, also the chemistry and the impacts on chemistry. We've all know that paper by Rosalovich. I think stratospheric observations, if SAI is anything that might become realistic, we want to have the observational capabilities to detect and monitor. And I still see some open gaps and things we need to do and push for. Thanks.
Thank you, Mark. Karen, go ahead.
Yeah, so just in relation to the talk we just heard was looking at what are the kind of limits that you potentially can detect. And so we probably do have measurements that uncoordinated deployments of a sufficient size, we would be able to detect. Whether we can detect something that has virtually no radiative significance or not, that's a whole other story, and we probably can't detect that. And then the question is, do we need to? But I think additional studies on figuring out exactly what we can detect, if emitting SO2 is going to be one thing, because first you end up with the gas, depending on the sensitivity or how much it is, how big of an area is covered. Something like tropomi can detect a large amount of SO2 that's being emitted in one grid box. So you could tell that something was happening. Whether you could actually sense that aerosol after the SO2 is formed into sulfate is another question. But then if you can't detect it, it's probably not having any radiative significance. But I think from the a geopolitical point of view, the various countries are going to want to know what's going on. So there definitely needs to be more research into that.
Thank you, Karen. Anyone else on this question?
There's one in the chat, in the Q&A box, Jean-Paul.
Okay. Can you read it, Mark, since you are there?
Yeah, it's by Andrew on does the recent chemtrails campaign in the US give hope for background measurement networks?
The recent.
I'm not exactly sure what campaign he's referring to, but
You want to unmute Andrew so he can.
Andrew,
yeah.
Andrew,
Yeah.
Go ahead. Yeah, Andrew, feel free to jump in.
We can just barely hear you.
Have you unmuted him?
Let's see. Okay, I said allow to talk.
Yeah, see, sorry about that. I hadn't been unmuted. There's a senator called Representative Marjorie Taylor Greene, who's been running a huge political campaign around chemtrails in the US recently.
Oh, you're talking about a political campaign. I was
Yeah,
thinking...
does it mean that we're going to get funding for the network? Because if they're going to ban chemtrails that don't exist, are they going to have to put a monitoring network in place? And does that monitoring network become useful for both background and observational measurements of any SRM that does take place? Even if they're looking for something that's, might as well be space aliens, dragons, or elves. It doesn't matter whether it's real. What matters is whether we get some money and balloons.
I don't think that the chemtrail populace is going to do anything other than look at the sky. They're not going to be monitoring anything in all the interactions I've had with various chemtrail folks. So I don't think that gives us any hope for background measurement networks. I don't know if anyone else has an opinion on that, but death threats, maybe I've gotten that, but
Yeah, maybe we can jump to the next question, which is about coordinating effort for summarizing existing measurements of stratospheric aerosol and their applicability to study potential SAI. There is a coordinated effort already by the stratospheric aerosol activity for summarizing stratospheric aerosol measurements. But now the question is a little bit different, is more like in connection with SAI, and what kind of, is there a need for some sort of overarching framework for doing that, or it's more like we have seen a number of studies and talks on Monday and one today about detectability. So it looks like people are already engaging in that topic.
so I would say one answer to that is that gets into your whole governance issue. If there's going to be, geopolitical agreement in doing SAI, there's going to have to be a coordinated effort to standardize the measurements, because country A may not like the measurements that country B is making unless there's actually been some political agreements as to what measurements need to be done. I'm thinking in terms of like the Montreal Protocol has specific requirements on reporting of emissions for different ozone depleting chemicals. So if there's going to be an international coordinated effort to deploy, there's going to have to be a coordinated effort to make measurements as well. But I don't think we're to that point yet.
Then let's move to the third question about natural analogs. We had some discussions already yesterday about that, talking about how volcanic eruption pyrocb can be used as natural analogs, and have we done enough mining on all those volcanic eruptions where I think some of them, the ratio between SO2 and ash varies tremendously. Some eruptions have very low ash content and mostly SO2. Some of them have way more ash, less SO2. And so the question is more like, do we think that there is still quite a lot that we have not learned from natural analogs that would actually prevent us or go against the idea of outdoor experiments?
Got a quiet crowd today. And Jean-Paul, I know you have an opinion on that. And I would say no, we probably haven't measured our natural analogs sufficiently. It's for one thing, we haven't gone out and measured very many volcanoes right after they've erupted, and that you learn something about the microphysics and dispersion. We can learn something about dispersion, even this isn't really a natural analog, but how rocket plumes disperse, how aircraft exhaust plumes disperse. Those are all things we still need to know before we can really adequately model the processes, the small scale processes that go on in SAI.
Yes, I mean, I fully agree. Nothing else to say. Now, the other question is more like, obviously, in a scenario where countries would agree on SAI, I mean, there were several talks, and I don't think Wake is here today, but there was also some concerns that one country may try. And so the question is, we are not, if nobody is aware what's going on, what could be very tricky is to differentiate, and that's maybe another reason why natural analogs are so important, would be to differentiate what and to attribute an SAI injection and completely rule out that no, it's not a pyro-CB. And we know that Dave Peterson presented a pyro-CB database, and we know those pyro-CB are very frequent. And so the question is going to be, if no one knows what's going on, how are we going to be able to distinguish what could be a small volcanic eruption or pyro-CB from a small SAI injection?
Well, something like a pyro-CB, your compositions are going to be different. So if you have, I don't think there's going to be a whole lot of SAI going on with black carbon or organic carbon. But it looks like Peng Fei has a comment to make.
Yes, I think this question is exactly what we want to address in Kat's paper, that to understand, to detect SAI, the key is to detect whether this signal is from SAI or from natural variability, like or other things like volcanic eruptions and the pyro-CB. So I think the key question is, can we monitor the current state, the natural variabilities, what's the natural variability of the strep aerosols in some latitude bands? And given that database, if this signal is like on the 90% or even 100% of your PDF, then you can determine, oh, this is something could be 90% of the SAI. Otherwise, then you can, I think that's something you can do that first. So the key is we have to do constant modeling, constant observations of the stratosphere aerosols and including its variability.
Mm-hmm.
And I just had another thought. This is kind of also related to Kai's talk. You know, he was talking about what levels of an injection are detectable. And I was thinking of, this is going back to some of your work, Jean-Paul, where you were detecting the atoll when there was low levels of volcanic aerosol. Do we have to start thinking about what is the background varies? So is it going to be easier to detect SAI in certain background levels of aerosol than it is after you just had a massive volcanic eruption that happened in the tropics? So, I mean, that's another thing that you can play around with models, but it's also something to be considered.
Definitely, yeah. Yeah, I mean, and I would add to that, I mean, since maybe a decade, we realized from small volcanic eruptions, now pyro-CB, now Asian monsoon, to some extent, compared to when people thought about SAI, the complexity of the stratosphere, I think, has increased. And so, and that's again, I think, going again, I'm not against the idea, but still pushing for more research, process or understanding level sufficient so that we know that if the background is or smoke, what's going to be the consequence of injecting SO2 into a smoke layer or something, or what's going to be if you are within the Asian monsoon, if there is already organics aerosol, what's going to have, how the organics are going to react to injecting SO2 and all those. So it is more complex that maybe people thought about 10 years ago.
I just have another quick point that for pyro-CB. So pyro-CB, particles are mostly accumulation particles, mode particles. So the size will not change from any Australian amplifiers. You can see that the effective radius is almost constant with time. However, volcanic eruption and SAI, you will go through a lot of size changes. So this may be a standard to detect it is a Pyro CB or SAI.
Mhm. That's why I feel also like Ben Kravis came up with those metrics of what could go wrong with and the probability of something to go wrong with our kind of understanding of what's going on. And I also feel like somehow those kind of metrics could be applied to natural analogs and putting those in some sort of areas where we, as you describe, understand maybe what we expect from the microphysics if we start doing something, an SAI in the context of a background aerosol with smoke and or an SAI with an existing volcanic plume. And I think that's where maybe the some coordination maybe or between SAA and the Lighthouse activity could actually be. We have another 3 minutes before the end of the discussion, so maybe we can go to the last question, which would
That's
be.
his hand up.
Can I just
Okay.
make a quick
Sure,
comment
go ahead.
here? I mean, we had 2 talks in the Monday session on balloon networks just being established, yours and Alex Barron's. And I think these networks, they can form a very nice basis. And at the moment, if I understand it correctly, I mean, what you do in France, and also we sometimes launch balloons with aerosol payloads here in Jülich. Typically, we wait for something that the models show us, a Pyro CB plume or volcanic plume to come here, so we can measure something interesting. But maybe we should aim to really do more background measurements as well, like to really regularly launch these balloons. Like I guess Terry Deschler, he launched his OPCs very often and regularly, so he could also see the background. And if we do that in several locations in the world, it should be possible to disentangle anything unexpected, like unsolicited SAI from volcanic or Pyro CB plumes. I mean, typically volcanoes and fires, they rarely go unnoticed. And so if we see aerosol where we don't expect it, that's when we should maybe raise a flag. Thanks.
So Mark, that was the whole point of
Yeah,
B2SAP.
Yeah.
We formed B2SAP to come up with a background. We wanted a background before there was SAI or a background before there was a large volcanic eruption or something. So at least, they're relatively expensive to launch, but if we do it in land areas, we get them back. So they're launched every month in Boulder. They're launched every month in New Zealand. And there's attempts to try to grow the network. We get 4 times a year in Reunion, some in Hawaii. So that network has been set up to be a background observing network.
That's great. Thank you.
I was about to reply to Mark about that maybe smoke should be relatively easy to distinguish from other things. I mean, if you speak to people like Mike Froman, it depends really when you are detecting an aerosol layer. And taking an example, if you are in the middle of the Pyro CB season, like middle of the summer in the northern hemisphere, you may have had 5 or 6 different Pyro CBs that affected the stratosphere, and that would be eventually transported too. So there is quite a level of complexities because of those multiple sources that could be kind of challenging if something happened in the middle of of the summer in the northern hemisphere, for example. if an SAI is injected in the summer in the northern hemisphere. Obviously, if there is SO2 detection, that's probably going to be the key. Any SAI with SO2 will be relatively easy to detect. I mean, from satellite perspective. Then the question is without SO2 and directly H2SO4, that's going to be way more complicated. Yeah. Benfei, yeah. And then we should wrap up.
Thank you. So I have another point is, so we talk about how to monitor SAI experiment. So through the study we are doing with Kai, so we are thinking, so not only to monitor SAI, but also monitor how the particles evolve, what's the microphysics. Do we really understand SAI as we basically just model it, right? So for SAI or everything. So we need actual data to show, okay, this is model is wrong, model is right. So also even though we know this is a plume, so we still want to measure that. So we still want to measure the microphysics. So this is how the satellite and the balloon ground data can be used to. I think this is also a framework for SAI activities. Monitoring activities are very valuable to future SAI experiment.
Mhm. Thank you very much. I think if I'm not mistaken, it's 2:50 here, 6:50 UTC. And then we have a small break before the next session, right? Mark, back to you.
Yes, that's right. We have a small break, and then Karen will chair the next session on SAI simulations with 2 talks and an open discussion. So see you in a few minutes.
Thanks.
Yeah, thank you.
So we'll try to start up again in a couple of minutes. I just want to check that Hung Wei is online.
Yes, I'm here.
Cool. So when Liwa comes back and can bring up the slides, we'll go ahead and start. And she's starting. So we've got 2 talks on SAI simulations in this session today, and this adds on to the talks that we had on Tuesday. And our first one is Hongwei Sun, who's going to talk about developing a pluming grid model for plume evolution in the stratosphere, which I think is super important. So I'm looking forward to hearing this talk.
Thank you, Karen. I guess I'll just start. And so I'm Hongwei Sang. I'm now a assistant professor at University of Hawaii at Manu. So this time I'm going to talk about, actually, it's a PhD work I did with Seb Sneezer and David Keys. So as mainly about developing a greater Lagrangian plume model and then couple the plume model into a global climate model, for example, so we can achieve a multi-scale pluming grid model. Next slide. So as an introduction, we know when we want to inject aerosol into the stratosphere to do the solar geoengineering, most likely we would like to use aircraft, and those aircraft plumes can be like 1,000 kilometers in length, but only several kilometers in its cross-section. So it's like a line-shaped structure. And also previous observation study have shown that this kind of line-shaped aircraft plume can stay in stratosphere for several weeks without with keeping its line structure. Next slide, next click. On the other hand, we know most global model have a resolution about 1 degree. Now maybe it's half a degree, but still it's too large to resolve this line shape aircraft plume. So this will cause, for example, underestimate the concentration inside the plume. Next slide. And we know that most nonlinear processes, for example, here give you a example of photochemistry inside the aircraft plume. We can see that there is a difference of ozone concentration when we use Lagrangian plume model versus conventional Eulerian global model. Next slide. So the problem we mentioned here is that for now, we find that conventional global climate model don't have like high enough resolution to resolve the subgrid plumes. As a solution, we created a Lagrangian plume model and then couple this plume model into global Eulerian model so that we can build a multi-scale pluming grid model. And this model has the ability to resolve the subgrid plumes even right after the aircraft emit aerosols into the stratosphere. Next slide. And this is a big overview picture of this model structure. And in the next slide, I will give you a detailed introduction. Next one. So initially, our plume model describes the aircraft plume with 3 parameters: the center location, the plume length, and also the plume cross-section. Next click. And we consider several physical processes. The first is movement, of course, is driven by the background wind. And next one. Next one is due to the ideal gas law, when the aircraft plume move to different location, it can be different temperature and pressure, which will change the plume volume due to the ideal gas law. Next one. Next one is the plume stretching. So we know that the wind field is not uniform everywhere. So there will be horizontal stretch, which can stretch the plume into larger lengths or even maybe shorter lengths contraction. Next one. Next one is plume splitting. It's like when the plume is split large enough, we would cut it into small pieces so that we make sure each pieces can keep a homogeneous status. Next slide. For the plume cross-section, we use adaptive grid. First, we use 2D grid to represent the concentration gradient along the cross-section. And then, next slide, When the plume is highly stretched, mainly due to the vertical wind shear, we would change the 2D grid into 1D grid to represent the plume cross-sectional concentration distribution so that we can save computer resources. Next slide. And when the plume is grew large enough, we have 4 criteria to decide when will this plume transfer from our Lagrangian plume model into the global model. So basically, so I will not go to details. Basically, it's like we have 4 criteria to decide whether the plume grew large enough. Next slide. Okay, so that's a very short description of the model development. Next slide. I would like to introduce some model results. We want to see with this plume model, how much improvement, hopefully we can have some improvement we can achieve by this couple model. So here we use 3D chemical transport model, JuiceChem, and we couple this plume model into JuiceChem. And then we do a 1-month simulation. We let one aircraft flying back and forth in one longitude as shown in the blue line there. And then this aircraft will continuously inject inert tracer into the stratosphere for 1 month. And the right figure shows you the after 1 month simulation with and without plume model, how the tracer concentration look like globally. So very straightforward. We can see on the top figure, there are lots of hotspots, which is a high concentration center, while on the bottom figure, we can see the concentration gradient are much smoother, which means that without plume model, we have a much smoother concentration distribution. To quantify this difference, next slide, we can plot the concentration PDF, the distribution on the top left. We can see that the right line shows you the concentration result with plume model. We can see it's several order of magnitude larger than without plume model. This is reasonable because as shown in the bottom left figure, we can see that without our plume model, the conventional global model cannot resolve the line shape aircraft plume, which will underestimate the concentration inside the plume. And we know that most nonlinear processes, next slide, are highly dependent on the concentration. For example, here we did a sensitive test. We applied the second order chemical reaction based on the inject tracer. From the left figure to the right figure, we can see that first, with the plume model, which is the top right figure, the product from the second order chemical reaction can be 2 order of magnitude larger than without plume model. And we also know that usually when we want to increase global models accuracy, we tend to increase the resolution. So we did another test as shown in the right bottom figure. We increase the horizontal resolution from 4 degree to 2 degree, 1 degree, and even half a degree. We can see with the increase of horizontal resolution, we can have an increase of product, but this increase is much smaller than the increase when we use the plume model. Let alone that when we increase the resolution, as we can see the x-axis, the CPU error is a huge increase compared with the copper plume model. So as a conclusion, next slide. Next one.
Hung-Wei, you're muted. Yeah.
Yeah, sorry, I think I just log out. Yeah. So
you go back one slide.
I think this is the one I want to talk. Yeah.
Okay.
Cool. Thank you. So as a conclusion, I want to say that hopefully we think this multi-scale pluming grid model can be a computationally efficient way to improve the representation of subgrid plumes, especially for the SAI. But of course, we also want to apply this new coupler model to different research areas, such as I list here, in addition to SAI, like just the typical aircraft plumes, or maybe even parasibia. I think there are some discussion in the earlier session. And yeah, that's all I want to talk. Maybe there is a next slide. Let's see what we have. Oh yeah, for next step. Yeah, so as you may notice, I actually didn't mention any aerosol microphysics here. I mainly focus on this couple model architecture and the physical process. And for the chemical and aerosol process, actually, that's our next step, as I list in the bottom right. We have postdocs working on that part, and also we also have another project working on accurately estimate stratospheric turbulence, because that can be an important factor influence the subgrade aircraft plume dilution, especially when, as I mentioned earlier, those aircraft plume can keep their line shape in the stratosphere for several days or even more than 1 week. So in that case, the stratospheric turbulence can be very important. And that's all I want to say. Thanks.
Thank you very much. And we'll have time for questions for this talk and the next one after the next one is done. So Pengfei, are you going to be giving the talk, or is your student going to be giving the talk?
I'll
You're
be
going to give
giving.
it. Okay, so this is injection near the stratopause minimizes the stratospheric side effects of sulfur-based climate intervention. And so this is Pengfei Yu's paper that I think is in ACP right now. Is that correct?
Yes.
Yeah.
Yes.
Go ahead, Pengfei, once your slides come up.
Sorry,
So,
Pengfei, is this your slides?
no,
No, that's
Liwei,
fine.
you have to keep on
That's-
going.
That's,
This is your
that's-
slides, Liwa.
yeah, that's you need to close this one and open another one. Thanks.
They should be after this
This is
talk.
it. There you go. Yeah, this is
Okay.
it.
Yeah. Thank you. Apologize. I got a flu a few days ago, so I might do not know what I'm talking about. But anyway, so this is a paper for so basically we come up with idea, say, okay, if we inject SO2 at stratopause like 50 kilometers, it might give you some different climate effect, especially the stratosphere environmental impacts from SAI. So this is basically a thought experiment. Next slide, please. So previous studies show that for the stratosphere, there are two major shortcomings from SAI. One is the stratosphere warming, because you inject at 15 or 30 degrees, then aerosols are accumulated in the low stratosphere in the tropics. That will heat the lower tropics. The heating itself can accelerate BDC or and impact on jets too, and also polar jets, and it will also strengthen the polar vortex, maybe leads to additional ozone depletion as well. So stratosphere, the tropical strat warming is one bad thing. Another thing is the Arctic ozone depletion. So aerosols are going to the polar region and will deplete ozone through heterogeneous chemistry. So that's long being discussed. Next slide. So first of all, we try to test the residency or the how much air. So we inject the same amount of SO2 in different lines: blue, black, and the red. Blue is 20, black is 25, the red is 50 kilometers. So you can see the 50 kilometers we have a highest IOD, which is not surprising, and because if you inject higher, then the lifetime is longer. But this is not the key benefits of SAI if we inject at 50 kilometers. Next slide, please. So why we inject 50 kilometers? Because because there's a mesoscale mesosphere's rapid circulation will transport traces from pole to pole very quickly at 50 kilometers also. So that's why we do it. So next slide, please. So look at the left panel showing the latitude distribution. Okay, the horizontal axis is latitude. The vertical axis is AOD. The blue, black lines are 20-25 kilometers SAI. So if we inject at 15 south, 15 north, so they will just so this is their latitude distributions. However, if we distribute release SO2 at 50 kilometers, that will give you a whole another picture. So if we inject at 50 kilometers, because the mesoscale circulation that I just showed you in the last slide, the SO2 will quickly be transported in the high latitudes and form aerosols when they are transported down. So that's the key difference. That's why we do it. Next slide, please. So by doing that, people worry about, oh, if you have more aerosols in the polar region, then will cause you more ozone cause you more ozone depletion. The simulation shows the opposite result. The left is 25 kilometers ozone tendency, and the right panel showing 50 kilometers ozone tendency. Okay, so the red means ozone increase due to NOx depletion. So if you have aerosols over there, then it will deplete all NOx through N2O5 hydrolysis, and depletes NOx and increase ozone. And in the lower panel, in the lower 12 kilometers in the polar regions, then you have ozone depletion that's due to normal heterogeneous chemistry. So comparing between these two panels, the 12 kilometers ozone tendency is roughly the same. However, if you, on the 50 kilometers on the right hand side, because it has lots of aerosols in the 20 to 30 kilometers, that aerosols will deplete NOx and increase ozone. So it turns out to be increase the column ozone. Okay, it doesn't mitigate the ozone depletion at 12 kilometers, but increase ozone upper. So the column, the ozone column is greater than the 25 kilometer injection. Next slide, please. So this is what we have done. Like the horizontal axis is South Pole October ozone column without geoengineering. The right hand side is, the vertical axis is the ozone with geoengineering. The red is the 50 kilometers. Basically, this is a very complicated figure, but anyway, so when CFC 11 decreases, you have ozone recovery. So this is what the figure shows. And also the second point is the red curve is always above the black curve, which means if you have 50 kilometer injection, then you have higher ozone, less ozone depletion compared with 25 kilometers, significantly. Next slide, please. Next slide, please. So now we're talking about ozone recovery, the depletion, the benefits. So 50 kilometers will give you less ozone depletion. How about the tropical warming? Next slide, please. So this is the TTL, the tropopause temperature. So the black line is the no SAG. The black dash line is 25 kilometer injection, and the red line is the 50 kilometer injection. So 50 kilometer injection, the TTL is warmed by only 50%. So with the same amount of injection material, so less TTL warming. Next slide, please. So this is the comparison between the warming between the 25 kilometers on the left and the 50 kilometers SAI on the right. So 25 kilometers, you can see the warming is concentrated at the tropics in the lower stratosphere. However, in the 50 kilometer case, for the same amount of SAI material injected, the warming effect is much smaller. Next slide, please. So because the TTL is less warmed, so which means less water vapor can get into the stratosphere. But by 25 kilometers, more water vapor can get into the stratosphere to compensate, offset the SAI efficiency, because certain water vapor is greenhouse gases. Next slide, please. So with 50 kilometers, you cool the pole more. How about the tropics? So this plot shows the surface temperature response between 50 kilometers SAI and 25 kilometers SAI. So two SAI, the difference between two SAIs. So in the tropics and the mid latitudes, there's no difference. So they cool the same amount. Maybe SAI 25 can warm can cool more in over the land, but it's not statistically it is not statistically significant. However, in the mid high latitude, because we have higher aerosols loading in the mid high latitudes in the 50-kilometer scenario, then it cools more. And on the right panel, it shows also, sorry, it shows, I'm supposed to show both an Arctic and Arctic CIs, but this is Arctic CIs, which is we are very interested in. So the blue line represents the CIs amount. CIs amount as a function of time. So September is the minimum, and for the dash line is climatology, and the red the short dash line 25 kilometers. Well, we saved ice using 25 kilometer SAI because it cools the Earth. However, with the same amount of SAI, with 50 kilometer injection, you save more. So so this is basically because you cool the pole and the mid latitude more, you save more CIs. Next slide, please. So this is a summary between the comparison of 25 kilometers at 50 kilometers SAI. I listed some advantages of 50 kilometer SAI over 25 kilometer SAI, including, okay, we have less warming in the tropics and more ozone in the polar regions, less ozone depletion in the polar regions, and less water vapor increase in the stratosphere, and less vortex changes compared with 25 kilometers. And also you cool the polar region more and save more sea ice. I think that's it. Thank you. Thank you very much. That's my start.
Thank you, Pengfei. We can leave this up here for a minute or so. Are there any questions in the audience about these last two talks, either the Plume grid talk or the 50-kilometer SO2 injection talk? And looking for hands. It looks like Moha, go ahead.
Thank you, Pengfei. This is really a nice
We
talk.
can't hear you, Moha.
Can you hear me?
Get a little closer to the mic.
Okay. Do you hear me now?
Yes.
Okay. So thank you, Pengfei. This is really a nice talk. I just logged in when you already a little bit have already started. I was wondering, have you also looked at the stratospheric circulation response and then the associated wave dynamics in these 50-kilometer injections?
Do you mean how the like BDC changes?
Yes, exactly. Yeah.
25, 2050?
W will start. Yeah. Sorry.
It will change less than 25 kilometers.
Okay. So
because the warming is smaller.
Okay, but the I mean, if I check the temperatures, you see, I mean, when you show the 25 kilometer and the 50 kilometer injection, the temperature in the stratosphere are a little bit cooler in the 50, I think.
Yes, because less warming for 50-kilometer injection. Yes.
Yes, but if I think like, okay, cooler stratosphere mean then a little bit faster BDC, or
because you're warming, you have circulation changes. I think that's the dominant reason, and you have less warming, so you have less changes. So that's what I think.
Okay, I would be interested in looking at the age of wave, what it look like differences, because
age of traces. We
yes.
haven't done that, but it will be easy to do. So
okay, yeah, I think that would be really interesting to check out the age of and because the W bar star is not really the full answer, because it's just giving you the upwelling, but you have the mixing that kick in, and this is more linked to the wave breaking that may change.
Okay.
Yeah,
that's more dynamic.
Yes, exactly. Yes.
Yes. Let's get in touch and see what happens. Yeah.
Okay. Thank you. Nice talk.
Do we have any other questions directly for Hongwei or Pengfei? So I think I have one that's just, I think you touched on this at the very end of your talk, Hongwei, is so you've done your simulations just with the tracer and not with the microphysics happening at the same time. So it sounded like that your next step is to add the microphysics to see what happens to the aerosols that are formed then?
Yeah, that's our plan now.
And I'm imagining that's a whole PhD project then. So we're looking at a couple more years before that's done.
Yeah, that's a good point, actually. Yeah, yes. I should have finished it, but yeah, it's take more time than expected to this development. Yeah, but luckily I think for the aerosol and chemistry part, because we plan use so we use JuiceChem. It is a chemical transport model. It has pretty good like chemical solver, KPP chemical solver. We can just call it as a function, so we don't need to develop by ourselves. And for the aerosol.
Go ahead.
And for the aerosol part, we will also just borrow the existing Thomas and I think it's APM beam science aerosol scheme. Yeah, that's our plan.
Okay. All right, thank you. Michael?
Yeah, hi. Good morning. Just a question. So, isn't it too warm that you build up there sulfate aerosols? I mean, sulfate aerosols, they evaporate at 30 kilometers, and then up there it's too warm. So you are looking for other kind of aerosols up to bring it out there, or?
This is to Peng Fei.
Thank you, Michael. Thank you for your comment. Long time no see, by the way. So we inject SO2 at 50 kilometers. Aerosol form like 20 to 25 kilometers instead of 50.
Okay. Then you.
So that's kind of a misleading for a lot of people. So we inject SO2, and the tracers are transported faster.
Yeah.
And the residence time is longer. However, aerosols are forming at lower altitudes. If aerosols form at 50 kilometers, it will evaporate, right? As you said,
sure.
right?
Yeah. Okay, thanks for the clarification.
There's also an interesting question in the Q&A.
I got to read too. Okay. So that was Peng Fei's last two slides that he didn't show you. Peng Fei, can you comment on how we get aerosols up to 50 kilometers?
Yeah. So yeah, I do have the technology right now, so but I don't. So we don't know. So I think a balloon seems the rocket is the only way to do it, and we have a co-author Martin who works closely with the aerospace, and seems the rocket reusable rocket is frequently used, and we have some estimate on how much rockets we need to use, and what's the frequency, and we also write it in the paper. So we don't know. So I personally don't know how we deliver that, but seems the rocket is the only way. And also he also mentioned for the future cargo point-to-point cargo delivery is a kind of interesting with the business interest. And then if we can do in lower orbit delivery at 50 kilometers, maybe it's useful. So I don't know. So yeah, sorry, Karen. Sorry.
I have a quick comments. So Peng Fei, I remember you have another paper like using black carbon to like raise up the aerosol. Do you think that can help you like reach 50 kilometers?
No, thank you for your question. So I didn't use any black carbon to do anything. So Australian wildfire use black carbon to self-loft. I didn't do anything, but anyway, so yeah, you can, you can do black carbon into the plume, and the plume will go up, right? So that paper, right? So according to our recent analysis, even though we inject only small part of black carbon will be sufficient to lift the SO2 into the stratosphere. However, the small black carbon will cause equivalent warming compared with the massive SO2. So we're still concerned about how much warming the cost by this lifting method. So we don't know. Thank you for checking out. So yeah, black carbon in the stratosphere is definitely not a very pleasant view. So we inject really small amount. And currently we are evaluating how much the black carbon will impact on the surface climate, how hydrologists know, and of the Tibetan Plateau, because we propose to do that in the Tibetan Plateau. So, thank you.
Any other
Well,
direct questions
do-
on? You go on. Go ahead, Fengfei.
Yeah, I do have a question for Hongwei. So I saw your paper. So we are writing a WMO report. So we want to highlight the plume scale modeling in our chapter. So through reading your paper, I found I don't know whether I'm right, because you also showed on your presentation, you compare with geoscam with and without SAI, with plume the PIG modeling, so plume modeling. Basically, I think the plumes or the aerosol distributions are basically the same, right? If I am understanding right. Or the budget, or the magnitude of aerosol formed in the geoscam with and without your PIG modeling.
Yeah, we do the same injection, so the mass is conserved. Is that what you ask, or?
Oh, okay. So the mass should be conserved. Okay, that's good.
Yeah.
So, and also the distribution, the plume, the how the aerosol distributed also looks similar to me from between these two. But only I do notice what you mean, that you have really high spot, right? High peak values that cannot be captured by the normal as geoscan, and you consider the secondary processes. I don't know if the chemistry or the physical dynamics process can be important. Someone just because we want to highlight that, so we want to try to understand more. So is that right? So the aerosol, general aerosol dispersion are not affected by the plume modeling.
I think it's affected. So I guess, yeah, I get you. You refer to the two plot like global map, right? Yeah. I guess I didn't show it correctly. I should show the difference. That would be a very clear difference we can see. Yeah, because I didn't show the difference. Only the two map looks like the similar given the distribution. But
And
if we
also,
show
also, I think plume modeling should be very important in the initial stage, like a week, 2 weeks, right?
Yeah.
A month in that stage. Maybe show that in that small in that early stage, what's the aerosol distribution or SO2 distribution? What's the difference between those two? And another point by your paper, I think, is if we inject SO2, there's not much difference. But if we inject solid particles, that's larger difference can be seen. That's from your paper. I'm not sure. So
no, because as Karen said, we don't really check the aerosol microphysics. What we mainly show actually is even we ignore the aerosol microphysics, we ignore even the chemical reaction, maybe just the fully dynamic and physical process, we can see a pretty clear difference. As I said, it's several order of magnitudes difference of the concentration. Yeah, I guess as you mentioned, we also want to highlight it's worth using this plume model to resolve the subgroup.
Have future work to explicitly say what's the 1 order, 2 order of magnitude difference at spot, the few spots mean something. Do you have some statements or
yeah, exactly. Once we couple the aerosol scheme, we will redo the simulation, including all the aerosol microphysics groups, and then we can see. I guess that's what we want is exactly, for example, particle size distribution, or maybe even the aerosol's radiative effects, the difference with and without couple plume model. Yeah.
Okay.
Yeah.
So it's good to know. So now I understand. So the traces are conserved. So the mass is are the same. Yeah, it's also, I think it's also good to test whether if we apply this model or if we don't apply this model, how the budget will be changed. I think that will be interesting. I think it's interesting to me. So So by using the
Oh, I get you. Yeah, definitely, because the thing can be different. Because if I would assume that in the plume model, because we have this high concentration, the concentration should be higher. So you probably have more faster microphysical growth can result in larger particle, which will have larger selling
that's
speed.
exactly what we are looking for. So if you
Yeah.
have more information on that, so I will write you email and get you in touch. Yeah, thank you.
Cool. Yeah, let's keep in touch.
Okay, so I think now we can move on to sort of the general discussion on SAI simulation strategies and scenarios. And I don't know, Mark, do you have the copy of that file I sent you? Because I can't share my stuff in Zoom without quitting Zoom.
Okay.
If you can't
Let
share
me,
it, it's fine, but
yeah, Liba, if you have it, you could share it. Otherwise, I will look for it.
it was just an email I'd sent to
Yeah,
him
it
earlier.
was just the one page, right?
It's just one page, yeah.
I don't think I have it. Just one
Okay,
here.
oops.
If you don't have it, it's not a big deal. I'll just read the stuff out. But so
No, I can probably share it.
Yeah,
Let me just open it.
so on Tuesday, we had 7 talks on SAI simulation strategies and scenarios. And then today we had these 2 by Hong Wei and Feng Fei. And we kind of covered a lot of topics, not necessarily all well organized. We had talks on scenarios, specifically what kind of possible spaces deployments could occur in, and then a talk on peak shaving. So Wake Smith talked about basically a polar deployment that you can do with existing aircraft that wouldn't require developing new aircraft to do the deployment. Then we had Pete Irvine talk about peak shaving, which is, you have CO2 increasing, and ultimately the thought is CO2 will start to decrease, and you're going to overshoot the 1.5 or 2 degrees or whatever. So you would, Pete's talk would then, he covered the how you would use SAI to bring that peak down. You still had to do SAI with current projections of CO2 increases. You still had to do SAI for a century at least. Patrick Keyes had a more of a philosophical talk on exactly how to design scenarios to explore various climate intervention possibilities. Doug McMartin was really talking about scales, how small, ultimately, what kind of outdoor experiments can you do that won't have basically climate implications, but you can use to learn about the processes that we need to know about. Gerald Fairley talked about an emulator that I think it was Reflective has online. I think his was the one that company was doing, where you can play around with, it takes a really long time to run your climate models for get enough statistical significance to know what's going on. They've come up with emulators for a couple of, I think they had Wacom and the UK model they had used to, so you can run it very quickly and you can run it online. Dave Peterson's talk was actually presented by Melinda Berman. Sorry, she talked about an inventory of pyro-CB and stratospheric smoke injections. To an extent, we kind of have to know what's natural and what's not natural. So this inventory he's got going goes from 2013 to 2023, has been published. There's actually data through 2025. And then Walker Lee talked about different ways that the ARISE simulations could have been done slightly differently, looking at various pathways, various scenarios. And then today we heard about the plume and grid modeling and yet another kind of scenario to do. So I think some of the questions that could possibly be discussed are what kind of scenarios do we really have to have done and run and understood with a variety of models before some intelligent decisions could be made by policymakers in order to make a decision about whether to deploy SAI or not, irrespective of starting World War IIIs and that kind of thing. That the models are not perfect yet, but part of the thing that had come up was depending on the strategy you use, and where by strategy it's essentially where are you injecting, you can get very different dynamical answers, different rainfall patterns, different cooling patterns. And so how many of these scenarios do we need to run to really give good information and good uncertainty? So I guess I would open up the floor to any comments that people have on that. And I'll give you a minute to think about it. And I guess we're working towards a really long break. And then, the other things in the SAI simulations ties in with the measurements that Jean-Paul just talked about. Is you use the measurements to improve the models so that you think you're doing something realistic. How close to realistic are we? How much can we believe what the models have done? And things like just combining scales, like was mentioned in today's talk, making the small scale then blend into the larger scale model, is a step forward. And are there any other thoughts on what kind of things need to be done to the models to make them more believable for the to present things to policymakers?
Yeah, I think, Karen, that also includes what was done in the first session on Tuesday on model capabilities and uncertainties, because of course these uncertainties in microphysics schemes that all translates to how sure or not sure can we be about what the models tell us, what the effects would be.
Yeah, and I guess I don't know whether I guess we kind of had discussion on that yesterday. And then I just had something on the tip of my tongue that I'm now forgetting. Analogs. So, most of the modeling talks we saw were specifically on different SAI scenarios. Do we need to be doing more modeling of these analogs that we can actually go out and measure to get better confidence in how the models are representing these processes? We've measured a couple of big volcanoes, not necessarily right after eruption, to get the whole life cycle of it. I don't think we've chased too many fire plumes, although that was what Dave Peterson's presentation was about, was a field campaign that's actually going to do some chasing of fire plumes. What other kinds of measurements do we need to get more confidence in the models?
I can add one comment here regarding the abbreviation, because when I developed Flume Green model, actually I do have the problem to validate the model, especially because it's like a near field aircraft plume. So we need to have observation to do that. But apparently there are not so many observations, especially right after the aircraft emission. So that can be a tricky part. I guess if we want to inject a huge amount of aerosol into the stratosphere, we need to know, like it's not only like we need to know how to design the aircraft to take those amount of aerosol, but also we need to have a better understanding, like right after releasing those aerosols, how for example, the aircraft engine combustion, the aircraft itself influence the aerosol dispersion, and also how the near field aircraft plume evolved within like the first several minutes, 1 day, or even within 1 week. So because for all those aerosol microphysics, that's non-linear, that's highly dependent on the concentration. If we don't have accurate observation, we probably cannot have like a accurate simulation, and that will introduce a bias, especially we have like continuous injection for local aerosols that can maybe a big bias. Yeah, can change the story maybe.
Yeah, great points. Thanks. Jean-Paul?
Yes, Karen. Actually, I put a question and a comment to Yang Wei in the chat and regarding volcanic eruptions, and we talked about natural analogs. Some volcanic eruptions sometimes simply don't inject one time an amount of SO2 in the stratosphere. The injection can be multiple pulses over extended or multiple time scale, and I think I have a couple of examples where the validation of Yang Wei's plume model by simulating, instead of an aircraft injection but a volcanic eruption, could probably be interesting. And I'm wondering how easily those kind of modifications in those models are possible. We have done geoscam simulation like after Raikoki or Onga with my colleague at Langley, but usually the injection, we do a very simple one grid point injection and look at the transport. And I think applying your plume model to volcanic eruptions would be kind of to me, potential natural step for validating your plume, the couple plume model and geoscam.
Yeah, actually, I'm typing the answer, but I guess I can just say now. Yeah, as Karen said, I think for SAI, general SAI simulation, we have like a volcanic eruption as a useful observation to do some validation. And I'm also consider using that for the pluming grid model, especially for the small volcanic eruption, which can give us some kind of filamentary structure, because after volcanic eruption, those kind of horizontal stretching can create some kind of line shape plumes due to those kind of horizontal stretching. So we will consider using that as the model validation. Yeah, hopefully it can offer some like observation perspective to our model. Yeah.
Yeah, I'd also like to comment on the point on natural analogs. Sorry for just jumping in, but I can't raise my hand while sharing my screen for some reason.
Fine.
I mean, we had the Hunga Tonga eruption, which may not be the perfect volcanic eruption comparable to SAI in many respects. But I mean, that happened at a time when our models, many models were very advanced in terms of aerosol simulations. And also we had all kinds of observations from space. We had campaigns with balloons going into the plume and measuring chemical, optical, microphysical properties. And there's this report that hopefully will come out very soon. And I think we should look at that very closely, because that can tell us a lot about how well the models compare to observations and what the shortcomings are. So I think, yes, we can definitely learn from the natural analogs. And in this modern era, I mean, Pinatubo would have probably been a better experiment, but back then, both the models and the observations, they were not in the state they are today. And so from that, we can learn where we need to improve in both observational and modeling capabilities. So yeah, I think that's almost better than any very small scale experiment in my opinion.
Yeah, and the Hunger report will come out in December. They're doing figures now. It's literally almost done. Actually, you could talk to Inez if she's online about what's going on with that. in spite of the government shutdown. We have people illegally working to finish those figures.
Great to hear that.
So do we have any other specific comments that you want to make about the simulation aspect? Unfortunately, we only have a few of our modelers here, not quite all the people that were speaking the other day, and I'm losing my voice. So we may actually take our break a little bit early if that's okay with Mark.
If there are no more comments, let me just stop the sharing of the screen so I
Okay,
can
that's
I can
Yeah.
see what
Oh,
happens in all the
Jean-Paul has a
boxes.
comment. Go ahead, Jean-Paul.
Yeah.
More like a general, maybe more like ethical question about, I mean, I speak ethical, maybe the question about performing simulations. Of course, I mean, that's a nice part of those simulations is we can inject at multiple locations, multiple heights, multiple species, but some high framework of research. Do we think, and that's an open question, do we think that there should be some limitations in an overarching kind of recommendation for not being too far from what can be an SAI, what SAI injection in the future? Meaning to say, the public perception of people working on some SAI is like very kind of thinking that people are a little bit imagining maybe too many ideas, ways to inject, and playing too much with trying to play too much with climate. So do we think that there's a need to kind of contain stuff, also the simulations on a kind of framework where maybe, I mean, we can't speak to a group who is deciding to do research on something. Research should be free. But at the same time, there are some questions about when we become more exotic in the way we do SAI injections in those models, how does it reflect and kind of translate into a public perception?
So are you trying to say, should we just be doing scenarios that we could potentially, like, in terms of these polar injections that we're talking about, that's using existing, you don't have to develop a new aircraft. It's something that could be done within, modifying existing aircraft. So there have been some simulations like that. Things that are injecting stuff in the tropics, or even, at 25 degrees north and south, we would need to modify aircraft. We don't have the equipment to do that. So should we just be sticking to things that we could do now, or things that might be realistic in 10 years if they actually do a development program? Is that kind of the point you're trying to make?
Yes, well, yeah, should we still stick to realistic scenarios? Yeah, exactly.
And I think from an assessment point of view, if ultimately a body like the Montreal Protocol came up and said we needed an assessment, they would probably want realistic scenarios.
Yeah. I see a question here in the Q&A box by Greg Slater, who basically says that besides all the modeling, actually calls it blind simulations, that we could probably learn more from small scale experiments. And even though that might already be relevant for the next discussion, I think many things, and I remember the talk in the impacts by Shrabani Tripathi yesterday, who presented this matrix of potential risks. I mean, there are some large scale risks, like really change rainfall patterns in Asia, which could cause big trouble for many countries and millions of people. And that's something we can never address in a small scale experiments. And we need these global models to point out these risks of any large scale experiments or deployment. And I think that's something very worthwhile, and we need to make sure we do these simulations and we reduce the uncertainties in predicting the side effects or even detrimental impacts that any SAI deployment may have, which we cannot see on the smaller scales. I mean, the smaller scales for microphysics and things like that, it may be helpful, it may even be necessary, we can discuss that, but I think these global models at the moment are a very, very crucial tool, and these simulations need to be made.
Yeah, I would agree with that. I think the other comment in that question is about, he says, I don't believe analog events have the precision to be adequate tests for validation. And to some extent, I would disagree with that. We can make really good estimates in a volcanic eruption of how much SO2 went up from satellite measurements. So I think those actually are precise enough to play around with validation. Jean-Paul, go ahead. Or were you just taking your hand down?
I will. Yeah, no. I was thinking, okay, should I keep it up or no? But because I just don't want to deviate from the topic. But about the small scale experiments ID, there is still one fundamental measurement that we're still, I think, struggling to do. I mean, people have engaged in, but Lagrangian measurements in any plumes. Peng was talking about the aerosol microphysics, and we have those single balloon flights usually give a snapshot, but really what is really lacking, I think, is to have Lagrangian measurements in plumes. And we don't even have that capabilities, and we have never implemented that kind of capabilities in natural analogs, in volcanic eruptions or pyrocb. It's usually either a single balloon or an aircraft, but an aircraft will not be able to follow the plume, and not, even if doing some cross section at a different time, it will not follow the plume for several days or several weeks to look at this evolution. And I think from a measurement perspective, if there is still something that I think where we're still lacking, and even considering a small scale outdoor experiment, is do we have a solution for looking at the plume, the microphysical evolution of those plumes as we follow them in a Lagrangian type of, not only Lagrangian, because we have to worry about sedimentation and so on. So it's complicated. We don't have, for the moment, I feel that a way to do it. I mean, we have at least never implemented it in any volcanic eruptions.
No, not in volcanic eruptions. I mean, we've done that kind of thing in following rockets and that kind of stuff, and following aircraft plumes. But Hongwei, go ahead.
Yeah, I have several points I want to say. First is like recall what Jean-Paul and Karen said earlier, like focusing on using existing aircraft technology to do like high latitude, low altitude injection. Also, another perspective would be like I feel like for now the SAI committee is kind of moving to new aerosol materials instead of sulfur aerosol. So maybe a similar question would be: is it worth to pursue a new material, or is it better stay with sulfur aerosol to have like even more solid estimation of the SAI with sulfur aerosol? And a second point I want to say is for Mark was said, like when we estimate the side effects or maybe the risk of SAI. Another thing I think some people have already done, like also worth mentioning, is the tipping point, which might worth checking how would SI influence those tipping points. And because those are like some kind of red flag, we definitely want to touch if we plan to do SAI. So that can be some like red line we need to check to make sure, like maybe even 100% sure that if we do SAI, we would not never like hugely influence these tipping points. And for the observation part, yeah, I agree that it's better if we can do some like small experiment, but I guess there are risks there. kind of almost impossible. Maybe I don't know. Maybe with global warming become more serious, we have the opportunity. I don't know. But I do agree, as we mentioned earlier, those like volcanic eruption can be some nature analog and maybe can be considered as some like nature experiment, and maybe we can explore more possibility to see whether we can use those natural case to validate our model instead of like doing the small scale experiment. Yeah.
Great points. And I think we have concluded our time for this section, and we'll do how much? 3-4 minutes? Is that what you wanted to take off, Mark?
Make it 4 minutes,
4
and
minutes.
then I'll convene the next session.
Great.
And so see you in 4 minutes.
Thank you very
Thanks.
much.
Thank you.
Okay, I think we are coming to the end of the break and to the final session of our virtual workshop series. which is on ethical aspects of studying and testing SAI. And we have 3 more presentations before we have an open discussion on these ethical aspects. So the first speaker in this session, that will be Javier Landes.
Yes.
Hope I pronounced that correctly. And that's
It's good.
On the ethics of an SAI mission-driven research. So please go ahead.
Thank you very much, Mark. Thanks, everyone. That's really a pleasure to be with you, especially for someone like me from Riga. So we are a little bit outside the main networks of research on SAI. And thank you to convene also this part on ethics, political question. I think it's super important. Next. Yeah, so I want to explain a little bit to you what I'm trying to do is that I'm really interested by those mission-driven research programs. And the question as a philosopher is how do they diverge, or they should diverge in terms of ethical rules that are applied to them. So what I'm trying to do is that when you look at the literature, what you notice immediately is that mission-driven research, as far as I could notice, it's not defined positively. There is always a negative definition. Its MDR is always defined in contrast to curiosity or investigator-driven research program. So that is first point that I hope to contribute as a definition. So I have this tentative definition that is written in the middle. MDR designates research programs that are explicitly aimed at answering questions, clarifying issues or uncertainties that are of direct relevance for policymaking. Moreover, they rely on a mechanism for centralized coordination. Actually, so my question, and again, it's a paper that there is no paper there, it's really early process. I'm really open to any feedback, comments, even people who like to jump on the project to participate, to write anything on that. So my question is how does the mission modifier change research ethics as in 2 dimensions. The first, the reflection, the general reflection on the morality of scientific research. And the second one that is a bit more applied, that is the enterprise of crafting regulatory documents like deontological or conduct codes. Next. So when we look more precisely, the mission, the use of mission suggests a mandate given by someone to someone else to do something. So MDR ethical quality, I start with this assumption, may be influenced by the properties of and the characteristics surrounding this mandate. So questions such as, what are the nature and content of such mandate? How is this mandate determined by and by whom? Should there be any deontological constraints, so prohibition, permission, obligation? On the content of that mandate, how is such a mission pursued? Under what normatively relevant circumstances like urgency or catastrophe. Next, please. So far what I could identify is 2 ideal types of mission. The one that is dominant is the scientific ideal type. You can find that, sorry for the typo, in McMartin and Kravitz, for instance, in this risk registry. So the kind of the goal there, and it's a process that is endogenous to the scientific community. The goal is, for instance, to reduce engineering or scientific uncertainties, to clarify specific climate impacts of deployment. So you have this mandate that is mostly endogenous to climate science and engineering. Next, please. The second kind of model that is less present in the literature, you can find it in an article that is at the end from Buck and Law, is a more social mandate. So questions to be clarified are mostly about socioeconomic impacts. So for instance, which injection strategy could primarily benefit the worse off? That's what we call maximum rule. You can even have mandates that are more granular. So for instance, how to secure poverty alleviation, food security, sustainable development, specific SDGs for a given group or region. So there the mandate is mostly exogenous to the climate science and engineering community. Next, please. That's my last slide, and I'm throwing a little bit question again to have your feedback and maybe we can discuss that. So those are the challenges or the issues to push with some questions I think are very important from a moral perspective. The first one is how and by whom the mandate is determined. So we can have several participants to that. It will be the policymakers, And that in that situation that raise issues of legitimacy, democratic legitimacy of those policymakers. Are they responsive to their constituency? Or we can decide to broaden a little bit the scope of the participants, to open that to stakeholders. That's a very common point that is made. And that raises issues of inclusiveness. So for instance, applying the principle of all affected parties. And also issues of contingency. So I'm reading there. What if it is too late to set up a full inclusive and participatory process due to some emergency? So that is something that should be included in this ethics of mission-driven research. Second idea of question, what about the freedom of scientific inquiry? And that's a question that emerged several times during the workshop. In principle, the idea of exogenously determined mandates create a tension with academic independence and exacerbate the risk of capture by the private or military sector. Third question, example of question, what about mandates, which researchers see with strong reason as morally problematic and realistic or vain? Do those mandates still constitute a mandate no matter what? Or can researchers override or relax some aspect of it in their wage condition? And that needs to be also included in an ethics of mission-driven research. Last question that is really morally central is the issue of axiological pluralism. We live in a society marked by the fact of pluralism. People disagree about the goals, how to achieve it, the goals of the good life. So how can mission be designed in a way that could accommodate moral diversity? Next slide, please. And that's the literature that I use. And thank you very much for your attention.
Yeah, thank you, Javier, for this interesting talk and for raising quite a few questions that I think are very relevant to the discussion we'll have. And with that, we go to the next speaker, which is Timothy Dali from Argentina, mainly on the language we should use to avoid confusions. So, Timothy, please go ahead.
Good morning, everyone. So yes, today I'm going to be talking about why we should clarify the language we use to talk about SRM research and non-research activities. Next, please. So yeah, these are just personal views of myself and my co-author. My co-author is Ignacio Mastroleo. He's the PI of a project that I'm working on. So next slide, please. So it's got quite a few slides. So this is part of a ARIA-funded project. So UK ARIA, this is a big injection of funding. So we're doing some ethics and governance as one of the 5 projects of the 21 projects looking at ethics and governance. We're focusing on concept and implementation of those concepts. Next, please. So when Confucius was asked how he would govern, he said he would rectify the names. That is, we should use language properly, because if language be not in accordance with the truth of things, affairs cannot be carried out on to success. And in the ethics and governance of SRM, we often talk about the governance of technologies, but you can't actually govern a technology. You can only govern the use of a technology to different ends. So those ends and identifying them is essential to the ethics and governance. Next, please. So basically, if what we say is not what we mean, then our ethical principles based on that terminology are wrong. If our ethics is wrong, our governance is wrong. If our governance is wrong, there is injustice and confusion, so we must revise our language. This is also the work of the Belmont report in the United States on the history of research ethics, this idea of research versus practice in medicine. So next, please. If we don't get the terms right, we are likely to misjudge what we agree or oppose to. So for example, I am opposed to all forms of geoengineering. We might have heard that, but actually people might have different views if they knew about the difference between research and deployment, for example. People might support policy that frustrates research. People might overstate risks and benefits by assuming that research and deployment are the same thing. They might fail to distinguish who is responsible for certain actions, such as researchers, policymakers, institutions, and it's also likely to weaken public trust in research, particularly. If we think that research means that we're going to start deploying, the slippery slope argument, the camel's under the nose in the tent idea, then people are not likely to support research. So they're not likely to support the production of useful knowledge. Next, please. So in the history of medicine, it was essential for basically for protections of human people to distinguish between research and practice. So it's useful to distinguish between research, which is about developing generalizable knowledge. That allows us to justify people, let's say, experimenting on human beings. We do it in the name of developing generalizable research. That's not the same as practice. When you have validated practice, you know something works. You give someone a vaccine because it's been tested and you know it's going to work in this population. Versus non-validated practice, this is also known as innovation. This is where we use a technique or a drug or an experimental therapy before we have sufficient validation for regular use, like off-label use, or when we have like emergency use authorization for vaccines in public health emergencies like Ebola and COVID. Next, please. So the UNEP has, in its one atmosphere document, has actually made some of these important distinctions. There are three things I'd like to point out. So they make this tripartite distinction between indoor SRM research, small-scale outdoor SRM experiments, and then large-scale deployment. But they don't provide an aim for indoor research, where we know that research has an aim. They don't distinguish between, when they talk about this word experiments, they don't distinguish between research and deployment, and they don't offer the possibility of small-scale deployment. Next, please. So we offer an idea of experiment, a definition of what we think experiment should mean for the purpose of improving public understanding, and a rhetorically neutral definition. So it's basically a deliberate use of an SRM intervention at any scale with either a research or a non-research main aim and without sufficient evidence. This idea, it's an experiment is when you're trying to, it depends on your goal, but you basically, whatever the thing you're using, you do not have sufficient evidence for its regular use. That's the key thing. It's an evidence-based definition of an experiment. We can do research experiments that we're trying to reduce uncertainty, or we can do deployment experiments. We're deploying something without even knowing if it works fully. Next, please. Sorry, so that's our definition, without sufficient evidence. Sorry, I thought I'd remove that slide, but we can go to the next one, please. This will become a bit clearer, hopefully. So basically, these are both experiments. ScopeX, so the research experiment with the small-scale outdoor perturbation trial of aerosols in the stratosphere. So that's a picture of Frank Koich. And Make Sunsets, they're doing this non-research experiment using experimental cooling credits. They're doing, they are both called experiments, but they're quite very different if you actually understand this point about terminology that I'm making. So next, please. According to the Geoengineering Monitor, the purpose, the aim of ScopeX was to develop a form of SRM known as stratospheric aerosol injection. This is incorrect. The aim was not to develop SRM. The aim, so if it had this aim, it would be an aim for deployment. So it would be implying that doing research is doing deployment, but no, ScopeX was a research experiment for the purpose of research. So this is incorrect. This is an idea. This is an example of unrectified terms. So this Geoengineering Monitor is misrepresenting the aims of the project. Next slide, please. The purpose of ScopeX was to improve understanding of the risks and also efficacy of SRM. So it's this idea of developing generalizable knowledge. That was the purpose of ScopeX. It was not to deploy. It was not about cooling the Earth. Next slide, please. However, we've written a critique of Make Sunsets. So Make Sunsets is claiming it has this deployment aim is to cool Earth, right? They are doing small-scale deployment. It's an experiment in the sense that they're not even, there is this idea, it's not fully validated as a thing, but the aim is to deploy, the aim is to cool the Earth. And however, this is an example of small-scale deployment. This is a US-based startup releasing small amounts of sulfur dioxide in these garden balloons, essentially. So we've made a critique of this. We've written a critique, Carabajal. So this is Maria S. Carabajal's paper, which in the European Journal of Risk Regulation. So if you just look at no governance is governance, basically arguing that the fallout, the media fallout, and the sort of government fallout, Mexico, intended to prohibit all forms of geoengineering, came from this really problematic scenario of there's various reasons as to why this experiment is quite criticizable, but it's very different to ScopeX. ScopeX is research, this is deployment. Next, please. So we're looking at our general sort of model. We're looking at translational science. You saw the analogy from the history of biomedicine. Well, we're trying to apply that to climate interventions in a more general sense. So the thing about translational science is that it's this idea of separating the wheat from the chaff, right? This is obviously a biblical term, but the whole purpose is that this idea of winnowing, right? You have some interventions that, when put together with the right information, will actually be like useful interventions, where some won't be, right? So the scientific translational process is not necessarily about producing an innovation. It's about knowing what works and knowing what doesn't work. So the chaff is the negative stuff. So it's either the harmful interventions or stuff that doesn't work. Whereas the positive findings are generally about beneficial interventions, what does work. And so you would have different actions based on your translational process. And we think it's important that we stress that, SRM research is about separating the wheat from the chaff. So we're trying to develop a translational model that comes from the history of biomedicine that we're trying to apply to climate interventions, because not all climate interventions will actually be feasible. have a favorable risk-benefit profile, etc. So that's the whole purpose of research, is to identify that. It's not to develop SRM, it's to separate the wheat from the chaff and find out what works and what doesn't work. And we believe that this process is a useful one. So we therefore are, encouraging this kind of development of research. Next, please. So basically, SRM discourse is an exemplary case of unrectified terms, as we saw on the geoengineering monitor. If we misunderstand and we misrepresent the aims of different activities, i.e. research and non-research, that leads to confusion, and that confusion will inevitably lead to some form of injustice. So, for example, I talked about Mexico intending to ban all forms of geoengineering because of what Make Sunsets was doing. That's for a whole different host of reasons, including various problematic non-engagement of communities, etc. So you can read our article on that. And basically, we're trying to give examples of where improving the ethics and governance of SRM research and non-research requires conceptual clarifications to do that. Next slide, last slide, just to say that these are about three projects we work on. One funded by the Degrees Initiative with Florencia Luna as the PI. So we're looking at health justice in the Global South. World Health Organization, looking at, again, health in the Global South. There's another Florencia Luna PI project. And then we're also part of this ARIA project where Ignacio is the PI and I'm the co-PI. And we're looking at ethics and governance of cooling research. Thank you.
Okay, thank you very much, Timothy, for this, I think, very helpful talk to clarify how our wording can really change our perception and how we are perceived by others. And with that, we move on to the final talk of this session and actually the workshop, which will be given by Yvette Ramos. And that's on SRM governance, I believe. So Yvette, if you're ready to start, please go ahead.
I'm ready to start. Thank you so much, Mark, and for the opportunity. Can you hear me well?
Yes, we can.
Okay, thank you. So good day to all, and thank you for the opportunity to share insights from my recent publication, co-authored with Professor Philippe Duarte-Sanche, entitled Are Climate Geoengineering Technologies Being Patented?, published in Climate earlier this year. Our study examines how patent data can reveal hidden dynamics of innovation and governance on SRM, particularly SAI. Next slide, please. Today, I'll highlight how our findings intersect with WCRP priorities on predictability, uncertainty, and policy integration. So why patent matters for SRM governance? Patents are often overlooked in the climate science discussion, yet they act as early indicators of technological intent and control. In the case of SRM and especially SAI, we discovered a surprising lack of explicit classification within the international patent systems, such as the WIPO and the European Patent Office. This absence of clear coding means that technologies related to stratospheric aerosols, delivery systems, dispersion mechanisms, reflective materials are buried under generic green or energy categories. From a governance perspective, this translates into opacity. We do not always know who is developing these technologies, where, and with what purpose. So in that term, this complicates predictability because transparency in innovation is a prerequisite for transparency in modeling, for example. Next slide, please. So under data source and methodology, we systematically reviewed the international patent databases, WIPO, ESPACEDET, using the international patent classification codes related to climate engineering, CDR and CRM, and cross-checked with the YO2C20 and C40 climate mitigation categories. Next slide, please. So three key results emerge. SRM specific patents are extremely rare, and when they exist, they are often disguised within broader environmental or energy classifications. Second, patent ownership is highly concentrated in the global north, United States, Europe, Japan, with a very limited filings from the global south. And third, private actors and university partnerships dominate, while government or public sector filings remain very marginal. So this imbalance matters because it influences who sets the research agendas and whose uncertainties are models. Next slide, please. When scientific models simulate aerosol interactions or climate feedbacks, they rely on open data. But if the key technical parameters like aerosol composition, delivery systems are locked within patents, our ability to validate or replicate models diminish. Therefore, uncertainty in SRM is not only physical or climatic, it is also institutional and informal, as actually we are seeing today in the workshop today. So it raises questions such as who controls the data underlying the models, who validates experimental results, and who would monitor the atmosphere in case of small-scale field trials. Reducing uncertainty in prediction thus requires integrating transparency mechanisms into both scientific modeling and intellectual property management. Next slide, please. Our paper concludes that governance cannot follow science. It must evolve with it. We propose that institutions such as the WMO, the UNEP, the WIPO, the World Intellectual Property Organization, headquarters also in Geneva, and the UNFCCC jointly design a global framework that establishes an open access registry of SRM-related research and patents, harmonizes the international patent classifications that do exist since many years to explicitly include SRM technologies, and ensures public reporting of funding and experimental data. Such coordination, we believe, would allow scientific modeling of SAI, for example, to be complemented by a governance model, one capable of integrating ethical, political, and social variables into climate projections. Next slide, please. So looking forward, 3 actions appear essential, as we say: create a WMO, WIPO, UNEP task force, for example, to connect climate data, IP transparency, and monitoring systems. Embed governance parameters into the Earth system modeling so we can evaluate not only climate outcomes, but also social implications. Build the capacity in least developed countries and small island developing states, enabling them to assess and participate in the SRM governance on equal footing. And to conclude, without transparency in innovation, there cannot be trust in prediction. Governing SRM requires that the capacity to observe the stratosphere be matched by the capacity to govern it ethically, inclusively, and globally. Thank you very much for your attention.
Thank you, Yvette, for this very interesting talk, which now concludes the session. And we open the floor to questions for the 3 talks first, and then we move to the open discussion. And I actually see in the Q&A box one question to Javier by someone, I can't see the name, which is, do you think the common binary of research versus development, I think that means deployment, and also the fear that more applied research would eventually lead to deployment, that this impacts how mission-driven research on SAI is perceived. So, Javier, maybe you can answer that.
I'm rereading the question. I mean, that's not my specialty because I'm a political philosopher, and because there we speak about public perception, right? So it's more falling in the field of sociology. So people like Bellamy, for instance, could answer that question better. But from a moral perspective, the fact that you have a mission, and the mission is really tied up to some specific effect that policymakers, for instance, they want to achieve, definitely that raise the bar about, okay, let's say the risk of slippery slope, meaning that you have those policymakers, they say, okay, you need to investigate how to achieve effect A, B, C. The research is going on, and we might consider that since there is this mandate, that will be easier for policymakers, especially because of the process of mission-driven research, how it is initiated, that the policymakers will just continue pursue to the deployment independently of what the scientists might be thinking. So if I understood correctly, I'm not sure that I totally replied to the question, but that will be my take on that.
Okay, thank you. Yeah, since I can't see the name of who asked the question, so there's a question in the chat to Timothy by, I think it's Gabriel. So Gabriel, do you want to read that yourself? Or
yeah, so essentially the
Yeah,
question
okay,
is very related to the one we just had for Xavier. It's about the slippery slope argument. I was just wondering whether Timothy can also comment on this based on his research.
So the question is, could you comment on the slippery slope argument often raised against SRM research, namely the concern that simply conducting research and showing it might work could increase the likelihood of deployment and reduce momentum for decarbonisation? I think that is obviously, I guess that is related to the sort of an empirical psychological question about human behaviour. I guess that's interesting that I guess the sort of working, I'll just make a few comments really. I can't really answer the question to a fully satisfying extent, but I think, and this does relate to what Xavier was saying about mission-driven research, is the fact that I think there is, at least in the philosophy of science, there's some work done by Interman, Christian Interman. She did work on the sort of on the fact that even when you do things like a model, you know, when you do basic research, the whole, let's say even basic research has, like, let's say, social, what we call non-epistemic, sort of non-knowledge driven considerations. Like, we choose to model certain things because we care about certain things. So even from the moment that you start choosing like a model to study a system and the impacts of an SRM scenario on a system, you're already making non-scientific choices because of things that people generally care about, right? Particularly in local context, like you'd want to know the impact on cattle in a region that depends on, you know, agriculture, for example, various aspects. So I guess the point that I would say is that actually, so when we talk about this idea of like SRM research, just by doing research, there's the risk of sort of moving to deployment. Well, you can, I think that's a question for empirical psychology rather than about sort of let's say the distinction between research and deployment. I would just try to say that we try to be as realistic with what research is, and we think that it is both a generalizable knowledge, you know, the quest for generalizable knowledge, but also has non-knowledge driven concerns within the questions that we ask, the research questions that we ask. And so that is a kind of paradoxical understanding of what research is. Like it's achieving, it can be used to all sorts of different ends. And one of those different ends is obviously not motivating the use of, you know, let's say reducing momentum for decarbonisation is a possible use of research by certain actors. But that's, again, I would say that's not the problem of like research ethics and governance. We tried to make these clear distinctions, and then it's kind of up to what society does with that stuff. Well, we want to have a clear framework, and then we basically aren't really sort of trying to make strong claims about the uses of the way that research and deployment get used within greater society. So it's not part of our, let's say, major concerns. We're trying to have a technical sort of approach to it without sort of saying what should be done with this. We just want to make those decisions clear so that the ethics is clear. But that does mean that, you know, ultimately that you know, good faith, bad faith actors could, of course, you know, hijack any system. That happens in medical research as well, even though the distinction between research and practice is very clear. For example, like it's still, people still cite observational research to make points about the dangerousness of vaccines. You know, you can always use research to certain ends, but ultimately we're trying to have like a clean, coherent system for ethics and governance within research projects for policymakers. That doesn't mean that, you know, that people with other interests couldn't, you know, take that nice tidy system and try and use it to show things that don't, you know, that it's not meant to be used for. And that is definitely a possibility, but that would depend on the intentions of the agent doing that.
Thank you.
Okay, thank you. Javier had his hand up for quite a while. So do you want to comment?
Yeah, a short comment, because I want also to leave the opportunity to Eva to reply to some question or just intervene. But there is something that was pointed out by you, Timothy, in your presentation that was very good. It's a bit of a frustration on the side that is not the scientific one, that is mine, that is as a philosopher, political philosopher, ethicist, is a kind of the merry-go-round criticism of SAI research, right? It's most of the time you follow the same pattern. So people will criticize research by, for instance, saying that SAI might lead to a termination shock. There, what you reply to that, you say, okay, we need to make a distinction between deployment and research. And there, people, critics, will mobilize a slippery slope argument, saying, no, but at the end of the day, the difference, moral difference is not that relevant between those two stages, because there is this kind of natural slide toward deployment due to vested interest and things like this. And my comment is the following, is that from outside, from someone that is working with arguments, like a philosopher, that's quite odd that very often we don't notice that a slippery slope has this particular feature to be, in many cases, a fallacy. So it depends on the empirical feature of your argument, but my point is to say that just mentioning the possibility of slippery slope is not an argument. It's coming with a very heavy weight of demonstrating that you have the possibility, if you accept A, you have to slide to B, you will have to accept C, and you will end up with determination shock. And the thing is that all those processes is often completely evacuated, and we end up discussing criticism just about, okay, is there a slippery slope, no slippery slope, with very little attention to those sliding steps that could be prevented with exit ramp, for instance, or any kind of check, a regular check on the research. That was just my comment.
Yeah, it's a very relevant comment. Yeah.
Thank you. And Yvette, do you want to reply, or should we go over to the...
Yeah, we can go over. I think there's, I cannot be the philosopher side, I guess. I'm a basic engineer, actually. But I do agree that, and we should continue, actually, my purpose was more on, and I know that the WMO and UNEP has done some efforts to go into those discussions this year. I was there as a virtual participant from the civil society, and we know that these debates are really taken off now, seriously, a little bit more seriously. So thank you for this discussion, really, thank you.
Yeah, thank you. With that, we come to the open discussion, and before we start, just a few words. I remember that we had a short session discussion on Monday, and some of the presentations there and the discussion that actually, I think what happened is what Timothy described in a way in his talk, that we were getting on the verge, to the verge of not talking about research, but about deployment and into pro and con. And I think what we all agreed on, and I'm sure we all agree on today, is that when it comes to climate change, that emission reductions should be our first priority, absolutely. But I think the view on how hopeful we can be that that will ever happen, or the perception of how close we are to the point where even if we cut emissions now, would cause a need to do more, that's maybe not a discussion we want to have here. We'd rather concentrate on the ethical aspects of the research. And one thing that was also mentioned on Monday is this share of the global south, that many speakers there said, okay, all the research is done in the global north, and the likelihood that all the decisions will be made here is very high. And for that, I think this UNEP, the two UNEP events in May and September, that was discussed there, and I think they were really helpful, and the recordings and the summary report of that is available, and I just pasted that in the chat. So if people want to look at that and get some idea of what was discussed there on the UNEP level, that could be helpful. And yeah, with that, I open the open discussion, and maybe one central question could be, which was addressed in the last talk on Monday, when or at what point are small-scale experiments worth pursuing? And I think we already addressed that to some extent in the earlier sessions today. So that's maybe something to start. But if you have another important point you want to raise and make, that's fine as well. So any hands, or just speak up or put things in the chat, feel free, please.
Well,
Timothy. Greg.
Greg
Yeah, I think. Yeah, we
can.
He wants to pick up on his earlier questions, probably.
Well, should I go ahead or wait?
Yes, please.
Okay. Well, I had a response or a question for Xavier Landes, I guess, and I was looking at his one. I think it was his second slide of 2 mission ideal types, scientific and social. And I believe in this case, in the case of what most of us consider a climate emergency, there is another aspect which I don't think is included in that, and that is that we have an ongoing catastrophe, basically. And so there's a body count that's an integrated body count that's accumulated. And so you are doing science in the face of a growing catastrophe, and you have to decide. So there's the question about the interventions. Are the interventions dangerous? Are they justified? This and that. But if you're in the face of a catastrophe, then you have to say how much do we have to triage, or do we have to face the fact that we are on we have a fuse here, and that we can't. These two mission types don't seem to have an endpoint necessarily, but there is an urgency in the catastrophe that must be acknowledged in the science. So I'd like to hear your response. Thanks.
Thank you very much, Gregory. I had that in mind when I mentioned that between parentheses, the catastrophe. It's exactly because of those catastrophe ethics or triage ethics. We have seen that during COVID, right? So there is a moment where actually you enter in a not normal functioning or operation. You are pressed by time. You have to make choices. Usually, consequentialist theory offers some kind of answer to that. So you are trying to reduce the harm. You have harm reduction approach, or you are trying to balancing out your uncertainty, your risk, and things like this. And my point is exactly what you mentioned. That should be included in even in code of ethics, or in the more general reflection about the ethics of research, especially for mission-driven projects. If we reach this point, we might actually have to suspend a lot of moral obligation that we consider were central in our conception of how research should be driven. So for instance, question about inclusion. We read all those very nice documents saying that we should include all stakeholders in the research. They should have a voice. They should have a part in crafting project. That's very fine. But if we are in the emergency situation, are we still bound by this daunting constraint? And to which extent we can kind of have some leeway and shift partly to what you have called a catastrophe ethics. That's totally, but that needs to be thought beforehand. And with arguments, we cannot just suspend things on the piecemeal base because we are just pressed by time. So yeah, definitely. Everything that you mentioned, totally agree. And that was partly the scope of my intervention.
Okay, can I quickly respond to that? I won't take much more time, but I would say that the way you frame it is you reach the point of a catastrophe or an agreed upon set of circumstances that constitute where you break from normal procedures. I think in this case, there is not necessarily such a break. There's just a growing set of catastrophes, a spectrum of catastrophes that are increasing, and every day you have to make this call. or you should. You are ethically required to make this call. You really, it's not. You can arbitrarily set if the body count reaches so much, or if the temperature reaches so much, but that's totally arbitrary. Or if the number of species lost reaches so much. Those are arbitrary definitions of a catastrophe, but they're not moral ones. What you have to do is on a daily basis. I mean, practically, that's not going to be a daily basis, but the community has to be assessing anew, continuously, because the situation is not predictable. It's accelerating. Or new things are happening. So you don't have the luxury of a bifurcation.
Yeah, I do agree. It's the notion of catastrophe. I will probably Timothy has something to say about that because it's about wording. But the definition of catastrophe is not widely agreed upon, might never be widely agreed upon. But no matter what, there is this kind of capture, this emergency shift, and especially toward consequentialist argument. I will leave other people reply to that.
Yeah, I can see Timothy's hand, but just one quick comment before that. I think, I mean, the point is well taken about the potential catastrophe and that we have to maybe act sooner rather than later. But I think when we do any research, we should still think about the aim and what will we learn from that research. So I think Jean-Paul made that important point earlier. If we do small-scale experiments, we need to have all the observational tools ready to really get an output out of that experiment. I mean, an experiment where we can't see the results, that would be pretty useless. So I think if we want to do research, we need to have the research tools. And I think in some aspects of SAI, both on the modeling and on the observational side, we're still lacking some tools that we need to develop. And that's, for me, that's important. Timothy, please.
Yeah, so I think this does relate very much to, as Xavier alluded to, with the idea of medicine. So, for example, there's lots of, there's no denying that there are some moments in time and certain contexts in which, a state of, for example, emergency is declared, for example, in the case of, the World Health Organization and the COVID-19, but, where I was living in France at the time, for example, in Marseille, there were treatments being used by in the name of a sort of catastrophe. People were sort of, let's say, reducing their thresholds, right? And that's what happens. You generally do reduce your certain threshold. It's all about trade-offs, right? You're always going to have to make trade-offs. So, for example, giving a treatment for COVID, right? The threshold, let's say, was sort of, even in public perception, was very sort of low at the beginning of the pandemic. We just need to sort of throw anything we can at this thing. But then there was this realization that actually, this idea of exceptionalism, I think that's what ultimately we were talking about, is this idea of exceptionalism. Like, should we, there's a period of, like, let's say, normal science, and then there's like a period for what this idea of like catastrophe science or whatever. But what we're trying to argue, and this is what governing bodies did quite well, I dare say, with like COVID vaccines, was this idea of like, okay, so normally we would, let's say, wait for four months post-trial to know what happened. Well, maybe we can reduce that to 3 months or 2 months to get like a vaccine not fully validated, because ultimately there's a full validation process in place, but we could maybe use an accelerated approval pathway for a certain vaccine, and that would allow people to have access to it, even though it's not fully validated. So that's an example of what this sort of exceptionalist thinking does, because it ultimately does reduce thresholds about risk benefits and timing. And what seems to be very interesting in the case of like SRM and is this idea of like a mismatch between research, i.e. validation. So, instead of talking about like the impact of SAI, for example, we're not looking at something that would have like an immediate impact. We're looking at something that you'd need to know. We need to do as much research as possible now, so that when this catastrophe that we're already going through gets even worse, we need to be able to have as much information about deployment scenarios as possible. So basically, that's why we need to do as much research as possible now, because there is a duty to research. There is a duty to research, especially during these kinds of catastrophes. Like, we need to know what works before we, as much as possible. That's obviously always going to be a little bit, there's always going to be gray zones, but we need to have as much idea about realistic scenarios as possible, so that when those moments came, you literally have to deploy something, in the case of like the COVID vaccine or whatever it might be, whatever kind of impact you're trying to have at like a public health level or a climatic level, you'd want to have as much information as possible, from whence the duty to research, and also this idea of like, yeah, so because of this mismatch that seems particularly problematic, right? We're not going to have like an emergency, whatever the sort of emergency. We tried like to have maybe like avoid an emergency deployment scenario where there's a lot of uncertainty. We're going to need a lot of time to know something's working. Let's do research now as much as possible so that we know what the scenarios are likely to be. That's kind of the sort of that would be the sort of lesson from medicine, I would say, right? There are these sort of emergency pathways in place, but they do rely on like a sort of match between the sort of pathways that you're looking at. Whereas it seems that in the case of SRM, you need time to know if deployment works. So we need to do research we need to establish research as soon as possible to make those the best guesses possible, basically.
May I respond quickly?
Sure.
Sorry about that. Yeah, thank you for that response. What I would say to that is, I mean, the way I see SAI being deployed, if it is deployed, it is going to always be in beta. We're always going to be learning because it's too uncertain. This is a too complex system, the humanity, everything. It's an incredibly complex system, and we have to be able to both opt out or continue at any point. So when you say we do all the research, this is the point I was trying to raise earlier. You say, let's do all the research so we can confidently say either go or no go. Instead, we will be research every day that SAI is deployed. We will be executing research because it's that complex. It's not a simple thing, and especially since right now we're simulating, we aren't experiencing the full complexities of the Earth system, of political, all these elements. So I am saying that SAI will always be in beta. And I think that's a challenge to both you and Xavier, sort of analysis. Thank you.
Yeah, Jean-Paul raised his hand, so you probably want to respond to that?
I wanted to kind of respond and comment on the analogy that Timothy has done, and that's I think the main point here is like SRM is not trying to treat really something or develop something against the root cause of climate change is emissions, and so the problem is as we divert from the main issues, which are the root issues, emissions, toward SRM, more research, we always feel like the way that the research funds has to be directed has to be prioritized at some point. And between emission capture and SRM, the question is, and that's a governance maybe question, is how should those three aspects should be prioritized? And I feel as researcher on stratospheric aerosols, I still believe that there is my personal opinion is that there is a priority based on fixing the root cause, emissions, trying to solve partially the problem by capturing, and then not really treating the root cause. I know the peak shaving idea is kind of trying to mix all three at the same time, but there is still the danger of undermining the root cause and say, okay, and not treating enough the problem, which are emissions.
Timothy?
So I will just paste a letter to the editor that I found because I'm doing a sort of systematic review of letters to the editor on geoengineering. And just to answer Jean-Paul's comment is that actually, so this is a point made by Robert Frosch talking in 2009, just saying that actually it's interesting that we choose to define geoengineering like the way we define geoengineering actually matters, because even though, for example, in the case of CO2 capture and removal, that actually would be an intervention from a sort of, again, an ethics and governance point of view. That would be its own intervention. And it's been And it's got, he made the claim that there's sort of a double standard there because it's seen as the ultimate good, removing carbon dioxide from the atmosphere, which is perfectly understandable. But that's not the same as reducing emissions. Capturing emissions that are already there would actually have an impact in other ways that there might even be a risk-benefit trade-off there. So I think that just stresses the importance of language here. So I think we all agree there's consensus that reducing emissions is the ultimate priority from a long-term, short and long, again, long-term scenarios especially, point of view. However, the way we define geoengineering, and it's generally pretty much consensually now, sort of seen in mostly as the SRM sort of stuff, that carbon capture and removal wouldn't itself be entirely, that would need its own ethics and governance, because there are also potentially even negative consequences from capturing carbon dioxide that's already in the atmosphere. It's not the same as again, from just a human action point of view, ethics and governance, it's not the same to, when you're assessing the actions of two agents, that one is reducing his emissions and the other one is capturing previous emissions. It's not the exact same thing, and you wouldn't want to confuse them from a sort of ethics and governance point of view, because there might be different risk-benefit trade-offs and different things to capture in your analysis. But even though, obviously, of course, I agree with the claim that we need to reduce emissions.
Yeah, thanks, Timothy. I just want to quickly answer also to Greg about that we will always be in beta. There was a very nice talk, which I think reflected exactly that on Tuesday by Doug McMartin about learning across scales, that we learn as we scale up and we scale up as we learn. But also there, the point was made that we need to have the tools to do that learning. I'm not sure, Greg, you were there on Tuesday, but I think that talk, at least it provided some kind of strategy how we could go up in scales without maximizing the risk or with minimizing the risk.
Yes, I absolutely agree. I did hear Doug's talk, and I agree with that approach. I guess I'm going a little bit further. I'm saying that even if you reach sort of a tentatively agreed upon scale of intervention, you're still in beta. You'll never be out of beta.
That's probably true.
Anyway,
I would agree with that. Yes,
I agree with Doug McMartin's strategy of and his strategy. I think, even if he didn't directly say it, is we can start soon with this, because he's talking about a ton or two first, and a ton has a vanishingly small chance of hurting anything or anybody. But you can learn about plumes, you can learn about this, you can learn about that, and all sorts of things, and you start uncovering assumptions that were incorrect, etc., and new physics, for example. So I think it argues for starting to experiment sooner. Even though I agree that you want you want a measurement system in place. You don't want to do it without a measurement system. And I think that I would agree, if that's the implication of your statement, that we have to have the tools prepared. I would count the tools as the measurement system. Yeah, you have to have that in place.
That was one of my main points. And at the moment, it seems that at least in the US, some satellites making important measurements of aerosol, of temperature, of all kinds of things, environmental measurements that are still in perfect conditions, designed to work for several years to come, may be turned off due to funding going other directions. And so I think that's something we need to solve before actually doing something, so that we can actually see what the plume does and how it affects temperature, chemistry, and things like that.
Well, true. I mean, the situation in the United States is a bit exceptional right now, but one may have to get by, if you're starting with small scale experiments. One may have to get by with in situ measurements, because they're cheaper than satellite measurements. Launching satellites, which may be difficult, and they also take a while to get ready and to launch. But I would just say, as far as the measurement system, the measurement for the smallest end of the spectrum of tests, you can get by with in situ measurements, because you know exactly where you've got to put them. And you also, with in situ measurement systems, you have better precision, I think, if it's done right.
Yes, I agree with that. Timothy, you raised your hand again.
Just given that Gregory just said, I think we should experiment. We should start experimenting as soon as possible. I'm just quoting. Just again, given the sort of distinction that I made between ScopeX and Make Sunsets, which is he talking about? They're both experiments, but one is a research experiment, one's a non-research experiment. I'm curious as to what he was meaning more specifically.
I'm sorry. Hello?
Yep.
Yes.
Are you posing a question to me? I'm sorry.
Yes. Just when Gregory, when you said, I think we should start experimenting as soon as possible. I'm curious as to whether you meant research experiments or non-research experiments, i.e. deployment experiments.
No, I mean, I'm not at all identifying Make Sunsets as a model. I mean, the only experiment that, I actually know these guys but the only experiment that they are doing is an experiment sort of in societal behavior in a way, or market economics. But in terms of an experiment to understand the effects of SAI, they're not doing that. So no, but small scale, and again, it's the instrumentation, it's the measurement system that is in place. That's where you get the knowledge from, and that's where what feeds back into your models and and modifies your strategies. And that's not being done with Make Sunsets. Yeah.
No, true enough. But I guess I would say that the program in which I'm part, the UK ARIA, I mean, there's a lot of empirical projects that are now moving absolutely towards that kind of, approach.
Yeah, I mean, ARIA is a legitimate funder of legitimate experiments, as far as I'm concerned. They're not going fast enough for me, but I don't question the legitimacy as a funder of scientific experiments of the ARIA project.
No, but again, there's the question of social license. So, for example, when there were protests the day of the kickoff meeting, it's controversial. Like in the UK, this is a very controversial program. So it's about trying to get that balance between as scientific progress as quick as possible, but also maintaining social license.
Okay, but I mean that raises an entirely different issue, and I think that issue is felt extremely heavily, which is we don't want to do things that alienates somebody or another. That really is a different aspect of this whole thing. But in terms of how you safely deploy a system, or how you give yourself or devise a strategy that allows exit strategies, that was discussed to some degree by Xavier, but that is an independent thing from a strategy, basically a psychological strategy of maintaining or of not alienating groups that could ban you or whatever, or even if you're looking at it as the crowd is the ultimate moral judge. Either way, that's a different aspect of it, as far as I'm concerned, than what we've been talking about.
Yep. Okay. Yep. Fair enough. But I guess what I would say is that it's certainly the way that ARIA is thinking about this is that they are trying to keep the crowd in their minds as they make decisions, is what I would say. So
I'd like to actually close the discussion now, as it is 1 minute to 9 UTC. So we're at the end of this workshop, but I think it was a pretty good discussion we just had, very open, and I think it's very relevant as well. And with that, I thank all the speakers, all the people who took part in all the discussions over the last 4 days. And as I've written in the email, we are considering making the recordings available to a wider public, but we want to get feedback on that. So if you have any objections, any concerns, please send it to the organizers so we can take that into consideration when making our decision. We'll also disseminate some of the findings, some of the discussions of this workshop via various tools and channels, and we'll provide means to keep the discussion alive in online forum or whatever. So we'll send more emails to all the participants. And at this point, I thank everyone. And yeah, please all have a good day or good night wherever you are in the world. And look forward to keep communicating with you all. Also on behalf of Daniele, who is not here because it's pretty much in the middle of the night for him. Thank you very much.
Thank you.
And